Hello, good morning. My name is Chibueze AJUONUMA. I'm a PhD student at the Life School of Civil Engineering at Purdue. I'm working with Professor Jan Oleg and Professor Kendra Ek. And we're here presenting the progress on our research on the practical implementation of superabsorbent polymers for internally cured concrete. An overview of our outline. We'll consider the research, or we'll do a research overview where we look at the goals, objective, and experimental procedure, then the materials, the methods, and as well as the concrete mix design. And we'll wrap up with the results obtained, where we're considering workability, the air content, and the strength characteristics. After which, we look at the Thermocouple temperature analysis of the Thermocouple installed in the slabs. The use of durable concrete is a promising strategy to mitigate global impact of cement production and utilization on the environment. As durable concrete, it helps reduce the maintenance cost, it increases the return on investment, and decrease the frequency of replacement of existing structures, as well as decreasing the carbon dioxide emission and energy consumption. Now, a major sustainable approach for doing this is through internal curing of concrete, which increases the hydration, the degree of hydration, reduces the shrinkage and cracking potential, as well as cracking potential of the concrete structures. And to achieve this, the best way to achieve this is through internal curing of concrete by using of by water entrainment, where we create water reservoirs within the concrete within the concrete matrix, which produces continuous and continued water supply for optimum hydration. And one such way to do that is by the use of superabsorbent polymers, which are popularly known as hydrogels. They are cross-linked polymers with the capacity of absorbing liquid as much as in comparison to their large volume of liquid in comparison to their own weight, thereby forming insoluble gels. They act as internal water reservoirs in the concrete matrix, as well as an alternative to lightweight aggregates for internal curing purposes. Some of the benefits are improved hydration, it reduces moisture gradient, as well as mitigates durability challenges such as drying shrinkage, unautogenous shrinkage, and scaling resistance by improving the strength and minimizing the near surface dryness of the concrete. Now, regarding this project, it's an offshoot of a previously conducted lab research we did, where we used the superabsorbent polymers in mortars, cement mortars, and some of the outputs where we were able to get the absorption capacity, the mixing sequence of using superabsorbent polymers, and some of the results we obtained were improved the mechanical properties, and also it reduces autogenous shrinkage and improved hydration. Now, for the research, the goal of this research is to determine the delivery method, as well as the mixture composition, and how it influences the performance of internally cured concrete mixtures containing superabsorbent polymer, that's commercial superabsorbent polymers formulation, and type 1L cement, and supplementary cementitious materials such as slag and nanosilica. To do this, our objective is for internal performance of evaluate the internal curing performance of the commercial SAP in concrete, and also we evaluate the practical field implementation strategy to successfully deliver and disperse SAP in concrete mixtures, and then conduct field trials to compare the strength and durability of SAP containing mixtures with externally cured ones. For the field implementation, we use the commercial SAP, which was packaged in a 1 pound dissolvable bags, and these bags is equivalent for 1 cubic yard of concrete. And for storage purposes, the dissolvable bags were also were stored in a waterproof bag, which the outer waterproof bag was removed before batching. And for the field trials, we cast the 6 slabs, 8 feet by 8 feet by 10 inches slab, and we did some beams for flexural strength, as well as shrinkage, some prisms for drying shrinkage, as well as some cylinders compression testing. And in order to evaluate the performance of the concrete mixtures under different curing regime, 2 of the slabs, reference slab and slab number 8 with 30% replacement of slag, were cured using a thin film curing agent, and the rest were air cured. Also, each of the slabs was instrumented with midway with a thermocouple to measure the temperature variation and temperature history of the slabs. And cores were extracted from the slab at 7, 28, 56, and 90 days. The materials used were the traditional concrete making materials, cement, fine aggregate, that's fine and coarse aggregate, as well as slag, admixtures, and then addition of superabsorbent polymers. The stipulated method by the SCM were used in most of our lab testing. And for the mix design, our target slump was 3 to 7 inches, and the target air content was 5 to 8% at a constant water cement ratio of 0.44. And for those practical purposes, no super plasticizer was used. And the batching for the sap, we added one bag of the sap for 1 cubic yard of concrete. Now we've talked about the research overview. Let's shift gears and talk about some of the results obtained. Regarding workability, the addition of sap reduced the workability, although for all the mixture composition, we were within the target air content and slump. Then these are some of the picture excerpts from the field trials. Then for flexural strength, the beams were tested at 4 days because we are looking at how fast the road, if you are used in a road pavement or bridge deck, how fast can they be opened for traffic. So at 4 days we tested the beam, and the flexural strength by the addition of sap also improved the mechanical property, the flexural strength. At 4 days we were able to get 550 psi, that's the mixture with sap. And from the index specification, standard specification for 2024, at 7 days the modulus of rupture at flexural strength was at 570. So with the use of sap, there's a possibility of opening the road 3 days ahead of time. Then for compressive strength, the incorporation of admixture, superabsorbent, the slag, and nanosilica improved the compressive strength at 14% at 7 days and 30% at 90 days. And also the addition of sap also improved the compressive strength by 54% at 7 days and 42% at 90 days. And the samples gotten from the cores were also extracted from the slabs on the from the field, and the trend was similar from the when we tested the cores, just that there was a slight decrease in the strength. We also try to evaluate the performance of the concrete mixtures under different curing regime. Here, the NC signifies the no curing compound, and the CC signifies the curing compound. And we're able to evaluate the different the mixes with a curing compound, that with internal curing, that's superabsorbent polymers. We're able to find out that for the addition of curing compound, it increased the compressive strength by 14% at 7 days and 12% at 90 days. But the addition of sap increased the compressive strength by 54% at 7 days and 42%, as high as 42% at 90 days. Then we look at some of the data obtained from the thermocouples installed in each of the slabs. We're able to find out that addition of the nanosilica, it decreased the slab core temperature by 13%, although the time to reach the peak remained unchanged. And for the addition of for the replacement of cement with 30% of the replacement of 30% of cement using slag, we also reduced. There was also a reduction in the core temperature of the slab, and but addition of sap decreased the core temperature of the slab by 16%, and the time for getting to this peak was reduced by 2 hours. We tried to evaluate the variation of the heat generated under different curing regime. We found out that for the addition of application of curing compound on the slabs there was no significant impact on the core temperature of the slabs, but the addition of superabsorbent polymers reduced the core temperature of the slabs. Now, in summary, some of the key takeaway we're able to extract from our research. We found out that the concrete mixtures using slab exhibited enhanced performance. This can be attributed to improved hydration due to internal curing, especially when we are comparing this mixture subjected to different curing regime. Also, the reduction in workability and improvement in compressive strength in the concrete mixtures, when we are added superabsorbent polymers, they validate the efficacy of delivering SAP using dissolvable bags. And also the reduction in, we also found out that there's a reduction in the core temperature of the slabs by the addition of 30% of by the replacement of 30% of cement using slag. And also we also found out that the incorporating SAP mixtures and cement replacement with slag improve the performance when compared with just the SAP alone. So it shows that there's the compatibility of SAP particles and supplementary cementitious materials as well as type 1L cement. Now, what are we trying to do in the future? We're considering some of the durability properties, where we look at the scaling resistance, the drying shrinkage, also do the microstructure evaluation and the air void analysis, and eventually we'll look at the CH contents using thermogravimetric analysis. Thank you. These are some of we acknowledge this research is sponsored by the Joint Transport Research Program as well as Indiana Department of Transport. Thank you very much for your time.